Take GPT-2, give it the prompt, "What is KV caching?" and ask for 1,000 new tokens on a Tesla T4. Now run that test 2 ways. With caching switched off, the reported mean time was 56.197 seconds. With caching switched on, it was 11.885 seconds, about 4.73 times faster. That is one experiment on one model and one GPU, not a promise that every model becomes 4.73 times faster. But it leaves us with a useful mystery. The model, prompt, and requested length stayed the same. So what did the faster run remember that the slower run kept rebuilding? To see it, we can shrink those 1,000 new tokens down to just 5. We begin with 4 token tiles. The model processes them and predicts a 5th. That new tile joins the row. Now the model must continue. With no cache, it does not process only the new tile. It feeds all 5 tokens through the model again. Inside each attention layer, there is one row of calculations for every token position. A row describes how that position gathers information from the tokens it is allowed to use. On the previous pass, the model had already built the rows for positions 1 through 4. On this 5-token pass, it builds those same 4 rows again, then adds the one genuinely new row for position 5. Append token 6, and the pattern repeats. 5 old rows are rebuilt so that one new row can be added. As the prefix grows, the model keeps repainting an old triangle just to extend it by one edge. Avoiding that repaint would explain the faster run. But reuse is only correct if a future token cannot change the ingredients the earlier tokens already produced. Rewind to the instant just before token 5 arrives. When token 4 is processed, it may use tokens 1, 2, 3, and itself. It may not use any position to its right. That rule is called causal attention. Information may flow from earlier tokens toward later ones, but not backward from a future token into the past. A causal mask blocks every forbidden connection. Now append token 5. Token 5 may look back at token 4. But token 4 still cannot look forward at token 5. So token 4 sees exactly the same allowed tokens it saw before. With the model's parameters fixed and the earlier tokens kept at the same positions, their layer-by-layer keys and values cannot change when a later token is appended. The same argument holds for every earlier position. This is why reuse is exact. The model is not assuming the past is probably similar. It is keeping states that were originally computed with the future locked out. Those stable states have 2 names, keys and values, and their different jobs explain what the cache must keep. Open one attention layer and send the whole prompt through it. This first prompt pass is called prefill. At each prompt position, the layer creates 3 vectors: a query, a key, and a value. The query represents what that position is looking for. Each key is an address the query can be matched against. Each value is the content retrieved through that match. During prefill, the queries do their immediate job and then leave. The keys and values are copied into 2 growing histories for this layer. Now, one newly generated token reaches the same layer. It creates a fresh query, key, and value. The new key and value are appended to their histories. The fresh query is compared with every accumulated key, including the new one. Those matches determine how much of each corresponding value is mixed into the layer's result. Only the new key and value must survive for a later token. The query, the match scores, and the layer result are used now, not accumulated as the standard KV cache. And every attention layer keeps its own separate K and V histories. In a common layout, each history has the shape, batch, KV heads, sequence, head dimension. Those axes mean which request, which parallel KV channel, which token position, and which numbers make up one vector in that channel. So the KV cache is not stored token text, past queries, attention scores, logits, or final model outputs. It is the per-layer history of keys and values needed by future queries. Now we can say exactly what this memory removes and what it does not. Return to the moment when the prefix contains 5 tokens. Without a cache, the model rebuilds attention for the whole prefix, every position against every position, with the forbidden future half masked away. As the prefix length grows, the surrounding calculation grows like a square. With a cache, the old keys and values are already waiting. The model computes only the newest attention row. That is the saved work. The old rows do not return. But look closely at the row that remains. The new query still compares with all 5 keys and mixes all 5 values. At token 1000, the new row reaches across 1000 retained positions. Add 1 past token, and the row gains 1 more comparison and 1 more value to read. Its attention work is linear in the current context length, not constant. And attention is not the whole model. The new token must still pass through every transformer layer, including each layer's feed-forward block, the per-token calculation that follows attention. KV caching removes repeated work for old positions. It does not remove the new token's journey through the model or its need to read the past. Keeping that past ready is exactly where the memory bill comes from. Let's price one exact example, a Llama 27B setup with one request holding 4,096 tokens. This model has 32 layers. In ordinary multi-head attention, each layer keeps 1 key and 1 value with 4,096 numbers apiece for every token. The cache uses FP16 numbers, so each number occupies 2 bytes. Start with 1 token. 2 stored vectors, k and v times 32 layers times 4,096 numbers times 2 bytes give 524,288 bytes. That is 512 kilobytes for 1 token. Now keep 4,096 tokens. 1 request times 4,096 token positions times 2 for k and v times 32 layers times 4,096 numbers times 2 bytes equals 2,147,483,648 bytes, exactly 2 gigabytes. That is cache memory, separate from the model's weights. Double the retained tokens, and this cache doubles. Keep the same history for twice as many active requests, and it doubles again. This is not a universal cache size. It belongs to this model shape, ordinary multi-head attention, and FP16 storage. Models with fewer KV heads store fewer KV vectors, and other precisions change the bytes per number. But the receipt exposes the bargain. The model avoids rebuilding old work by keeping 512 kilobytes of reusable state for every token in this particular setup. Each way of lowering the bill must change one of these factors or move the bill somewhere else. The receipt has separate factors, so let's pull a different lever on each one. First, fewer KV heads. An attention head is 1 parallel attention channel. Ordinary multi-head attention gives many query heads their own KV heads. Grouped query attention lets groups of query heads share fewer KV heads, while multi-query attention shares a single KV head. Fewer KV heads means fewer key and value vectors per token. But this is a model architecture choice that can affect quality and compatibility. It is not a free switch for any pre-trained model. Second, quantization. Keep the same logical KV numbers, but represent each one with fewer bits. That lowers the bytes per number factor. Converting between representations adds work, so a smaller cache can still be slower when memory was not the bottleneck. Third, a sliding attention window. Some layers keep only the most recent fixed number of positions. Once the window is full, a new position pushes an old one out, so those layers stop growing along the sequence axis. The model must be designed to work with that restricted history. Finally, offloading. The logical cache stays the same size, but most layers' states move from GPU memory to CPU memory until needed. That frees scarce GPU space, while moving states back and forth can lower generation throughput. These levers do not mean the same thing. One stores fewer vectors, one uses fewer bytes per number, one retains fewer positions, and one keeps the same state in a different place. Each pays a different price in model design, quality, latency, or compatibility. And even after the amount of valid KV state is fixed, a serving system can waste memory in the empty spaces around it. Suppose GPU memory reserves one long, continuous region for every request's maximum possible cache. Real requests do not politely use every reserved slot. One finishes early and leaves an unused tail. Another ends and leaves a gap between two live requests. The slots are empty, yet a new request may still be unable to find one continuous region large enough. This is fragmentation. Memory exists, but its arrangement makes part of it unusable. PagedAttention changes the arrangement. It divides a sequence's KV history into fixed-size logical blocks. A small block table maps the sequence's first, second, and third logical blocks to any free physical blocks in memory, even when those physical blocks are far apart. Generation allocates another block only when the current one fills. During attention, the new query follows the block table and reads the earlier keys and values in their correct logical order. The physical addresses no longer need to be continuous. Notice what did not shrink. Every valid token still has its full key and value state, and standard attention still reads that retained history. Paging removes unused reservations and unusable gaps around the state. It does not compress the state itself. That can let more request histories coexist in the same memory. But it is not a universal paging speedup claim. Reported serving gains in the 2023 evaluation came from a system combining block-based kernels, scheduling, and cache management, and the mapping itself had overhead. Now return to our two clocks. 56.197 seconds without caching and 11.885 seconds with caching in that one GPT-2 test. The faster run won because it kept exact, causally reusable KV states instead of rebuilding the past. The price was memory that grows with every retained token and active request. That is the whole bargain. Keep the past to save computation, reduce real state only by changing what is stored, and use careful allocations so empty gaps do not consume the memory around it.